Hello and welcome to this special Nomira class. Today I want to teach us about hybridization. Hybridization is about mixing of two or more orbitals to form new set of orbitals. Okay, the new orbitals that are formed are called hybrid orbitals. Then what are these orbitals? We have the S, we have the P, we have the D, and we have the F. All right, now we are going to be focusing on the S and the P. The S is the spherical block or spherical series. It represents the shape of that orbital. The P is the principal, then the D is the diffuse, then F is called the fine series or the fine block. Okay, so we are going to be focusing on these two orbitals, the S and the P. All right. Under the quantum numbers, you can easily tell the number of electrons that can fill each of these orbitals. This one is filled by maximum number of what? 2 electrons. This one is filled by maximum number of what? 6 electrons. All right. Going forward, you have to be adding 4 to give a subsequent maximum number of electrons to fill subsequent orbitals, making reference to the diffuse series or block, which will be filled by maximum number of 10. That is adding 4 to 6, you have 10 electrons. Then the final one, which is the fine series, you have maximum number of 14 electrons. So let us focus here. Now we are going to be considering carbon with atomic number of what? 6. Using the old method of electronic configuration, we have 2 and 4, meaning that what? Carbon is tetravalent. Using the new method of electronic configuration, where you are seeing the SPDF, these things, when forming the new configuration, you adopt about 3 rules. We have the Pauli's exclusive principle, we have the Hund's rule, and finally we have the Aufbau's principle. We are going to be looking at carbon, which will give us 1s2, 2s2, and then 2p, 2. This arrangement is guided by the Aufbau's principle that states that in filling up of electrons in the orbitals, you have to fill in the increasing order of their energy level. Okay, so but memorize this. This is how the ground state of carbon appears in the electronic configuration. Okay, so for us to understand hybridization very well, you understand that something happens in this s orbital where one of these electron jumps and enters this p orbital. When an electron from a lower energy level jumps to a higher energy level, we call it excitement. We say that that particular configuration is in the excited state. Okay, that will give us something like this: 1s2, we have 2s1, then we have 2p, y will be 1, then we have 2p. Okay, this is x, y, another 1, then 2p, z will be 1. It means that at the ground state, it was supposed to be only 2 electrons on this orbital, but since one of these lower energy electron jumped into a higher energy level, it means that this is the excited state of this configuration. Okay, so we are going to be seeing how one of these s orbital, which is now unpaired, will be hybridizing with any number of these p orbitals. So for SP3 is formed when one of these unpaired s orbital hybridizes with the 3 of these p orbitals. SP2 is formed when one of these s electron pairs or mixes with only 2 of these p orbitals. Then SP1 or just SP forms when S pairs or mixes with only one of this what? P orbital. So that is the basis of hybridization. So right now, let me show you how they hybridize using the examples I have written on the board. For the SP3, you are looking at 4 bonds that are attached to this central carbon. Okay, now it means that for this particular orbital to actually meet this other one, there is an attracting force that will keep on pushing this to this. The idea of hybridization is about 2 unpaired orbitals to actually mix or fuse so that they will become one. They have almost the same energy or equal energy. Okay, so this will continue to move until it comes to a point like this and forms something like this. In other words, you have something like this, and then you have something like this. This is something that will form after this other unpaired orbital is trying to approach this one. Okay, and then there is a little angle that is formed between this and this, then creating a huge gap, which we call the bond angle. Here is going to form 109 degree 28 prime. This bond angle will be formed here, but in reality, what actually happens here is that this and this becomes equal as a single energy. Okay, why other ones try to adjust so that this same value for this bond angle will also exist here and exist here. So the shape we are seeing here is called the tetrahedral shape. Okay, let us look at what happens in the case of ethene, which has the SP2 hybridization. At this point, 1s orbital is hybridizing with only 2 of the p orbitals. You know, there were 3 orbitals for the p. Then in this case, s is mixing with only 2 of them. Okay, so we have an assumption here where there is about 90 degree at every point. Okay, so we are assuming this. Okay, so there is 90 degree at all points. Okay, but then the orbitals existing at this point will be trying to approach this other one. Okay, creating a bond angle of 120 degree. It means that each of these angles that were originally 90 degrees actually have about 30 degree on this side and 60 degree on this side, 30 degree on this side and about 60 degree on this side. So when you add 60 and 60, it gives you 120. The same thing happens on this other side. Okay, so this forms a planar shape. Let us see what happens for the ethene. In this ethene, we have 3 bonds and 3 bonds between the 2 carbon atoms. Okay, these other ones are existing linearly. So we have a linear shape here. Linear shape meaning that there is 180 degree between this particular bond and this particular bond. So there is no actual hybridization here. If there was, it can only exist between 1s orbital and 1p orbital. So there is no attempt for the unpaired p orbitals to try to mix together. Okay, thank you for watching this wonderful video. I hope you enjoyed the video. I hope you got something. If this is your first time of watching our videos, please kindly subscribe to our YouTube channel